look at today? Or particular types of questions, or you want to look at the free response, Allie? 16 on 21, yeah. Oh shoot, they're out of order, aren't they? Number 16. This one? Yeah. Okay, so this has to do with the interplay between the angular momentum and the kinetic energy. So just remind you of the equations for those, that L is equal to I times omega, and then also that the kinetic energy is 1/2 I omega squared. So if they have the same momentum, but the radius of disk A is twice the radius of disk B, that means that the moment of inertia for disk A is how much bigger than the moment of inertia of disk B. I'll remind you of the equation for the moment of inertia, that moment of inertia is the sum of mr squared, or for a disk, it's going to be 1/2 mr squared. What I'm really asking, though, is what is the relationship between I and R? So if disk A has twice the radius, that means it has how much bigger or smaller moment of inertia? A factor of 4. So the moment of inertia is 4 times. That is that the moment of inertia of disk A is 4 times the moment of inertia of disk B. That means that the angular velocity of disk A is 1/4 the angular velocity of disk B. You'll see where I get that from? That if I is 4 times the moment of inertia, that means that omega is 1/4 the moment of inertia. Because both disks have the same angular momentum, the product of I and omega has to be constant for both of them. So when one of them gets a bigger moment of inertia, it has to slow down. That's sort of like the figure skater, when she throws her hands out, right? She increases her moment of inertia, so her angular velocity decreases and goes down. Her arms out, I goes up, omega goes down. All right, so I'm asking now, what is the angular speed of disk B? Well, it's 4 times the angular speed of disk A. Right, was that the answer? A is the right answer? Yeah. So I want to know what is omega B. If I just solve this for omega B, it's 4 times omega A. So A is the right answer there. You won't have that question in particular, but I'm pretty sure there was a question that plays on that with the angular momentum and the rotational kinetic energy and how they differ. And you have to go through that process of, well, this is bigger, so this is smaller, and then by what amount is it smaller? We had some sort of different questions before where we've actually dealt with this quadratic relationship. It's a good question. All right. What else? Specific questions y'all have, or specific topics that you want to do, or if you want to do the free response. Absolutely. Okay, so this is similar to that previous question. Remember, again, L is equal to I times omega, and the kinetic energy is 1/2 I omega squared. It's spinning at a constant rate. It has a rotational kinetic energy E. Then it increases its moment of inertia I, and because of that, its velocity decreases by a factor of 1/2. Now, I omega has to be constant. So if the angular velocity goes down by a factor of a half, that means the moment of inertia has increased by a factor of 2. Because L remains constant, it has to stay the same. If omega goes down, I goes up. So now I want to know the new kinetic energy. Well, kinetic energy is 1/2 I omega squared. I have doubled my moment of inertia, and I've halved my angular velocity. So I have a factor of 2 times a factor of a quarter. 2 times a quarter is 1/2. So I have my energy is 1/2 what it was originally. Again, a good question. You're going to have a question similar to that, I'm pretty sure, on the exam. But those are difficult to work through. I get it, because you got to think about an inverse relationship with I and omega, and then also a quadratic relationship between the kinetic energy and omega. In general, if I'm speeding up, then that means that my energy is bigger. If I'm going slower, my energy will be smaller because I have that quadratic relationship. Alrighty, what else, y'all? Yeah, Nelson?
How does it go up on 1/2? If after you do all the math, you get 1/4.
Oh, I see what you're saying. So, because you're talking about this half right here, right? We'll do a half times 2 times a quarter. What I really want to know is what happens to the variable, because the kinetic energy is equal to 1/2 I omega squared. Maybe it'll help if I do it in a different color. If I increase this by 2 and decrease this by 1/2, then I have whatever I do to the right-hand side, I also have to do to the left-hand side. So I have to have a factor of 2 over here, and I have to have a factor of a 1/2 squared, which is a quarter. See, what I do to these two, I have to do to this as well. So 2 times a quarter is a 1/2. So I'm not really worried about this. This is just a constant. This doesn't affect the change in the energy at all. It's a good question. That's not the first time I've gotten that question. I've seen other students make that mistake. Is that clear? Yep. All right. What else, y'all? Yeah.
You number 17.
22? Okay. Yeah, so you'll have one, at least this is on the free response. I don't remember if I put it on the multiple choice, but at least it's on the free response, where you have to look at a manometer like this and tell me what is the relationship between the two pressures. And it all has to do with the levels. The one that has the lower level is the what? The bigger or smaller pressure? Right, it's the bigger pressure. So if I have a manometer, let's do it on open on both sides. If I have a manometer that looks like this, where the fluid's this way, that means that this pressure, P1, is bigger than that pressure, P2. The lower level is the bigger pressure, because you can imagine that this pressure is bigger, so it's able to push this fluid down and push it up into the other side. Now, in this case, look, the levels are the same. And so if the levels are the same, that means that the pressures are what? Also the same, right? So in this case, P is equal to P naught because the levels are the same, right? Again, I don't know if that's in the multiple choice. I don't think it is, but it's definitely on the free response. That's the third or fourth question, where you describe what is the relative sizes of the pressures, which has the bigger pressure. That was I think last semester, that was the argon gas problem. Okay? Particular questions? Yeah, okay. 17? Yeah. So this is like a manometer, but it's a barometer. Still, I'm going to have P is equal to P naught plus rho GH, or it's actually P naught plus or minus, right? But in this case, P naught, or I call it P2 here, that this is equal to 0. Don't be blown away. Don't be, what? confused by using a P2 here. The P naught is really just your known pressure. Whatever your known pressure is, that's probably what was confusing you, right? That I had P2 there instead of P naught. P naught is just my known pressure, and in this case, that's equal to 0. Look, if P1 is 1 atmosphere, and this is filled with water, y'all remember what the height of a column of water is at 1 atmosphere? Huh? It was pretty big. Yeah, it's not 15, it's 10 meters. Remember, that was the first barometer that that guy was named Kelly, I think, that he built back in the 1700s. And it was different. He used wine, but a similar density of water. That it was difficult to build because you had a column of water that's 30 feet high, and it's just hard to build that. So, but anyway, I can calculate it. P is equal to 1,000 times 10 times h. Here, P is 1 times 10 to the 5th, and I solve that for h, and I get h is equal to 10 meters. So B is the right answer. Have a problem like that? In fact, you have a problem like all of these. I don't know if you had to calculate h. I think you might have had to calculate P. All right. What else? Yep. Can we look at number 19? You do have one of these. These aren't difficult. I was working with a student earlier, and it's just sort of practice doing this in your calculator because you have two numbers with scientific notation on them, and if you're not careful, you'll get the order of operations wrong in your calculator. So if you have your calculator, you might want to just sort of go through it with me right here. So I know that F over A is equal to Y times delta L over L. And I give you all these things. 1960 over A, which is 7.1 times 10 to the minus 6, is equal to Y. This is for copper. Oh, look, I have it right here. 11 times 10 to the 10th. It will not be on the same page, that Young's modulus. It will be on your equation sheet. So just beware that you're going to use those tables quite a few times. And then delta L is what I'm looking for. That's the increase in length. And then the length is 2 meters. The length is 2 meters here. And then I solve for delta L. You probably want to rewrite this because if you try to solve this in your calculator, you're just going to have some difficulties. I want to multiply both sides by 2 and divide both sides by 11 times 10 to the 10th. So it's going to be 2 over 11 times 10 to the 10th times this thing on the left-hand side. That's 1960 divided by 7.1 times 10 to the minus 6. And that's probably easier to put in your calculator looking at it in that way. I really recommend that you write it out on your page when you're just solving this. It's not hard to solve. Like, y'all can do it. It's 8th grade math, or 7th grade, 6th grade, I don't know. But, you just want to compute that number. It's either A or C, right? I don't remember. Which one was it? I don't remember. Did y'all calculate this? What is it? C. So it's 5 times 10 to the minus 3 is what you get.
No, I got like 17. 17.
All right, y'all make sure you can do this on your calculator. Number 19. Yeah, see. So this calculation should come out as 5 times 10 to the minus 3, or 0.005. Just be very liberal with your parentheses so that you make sure that you get all these scientific notations correct. You can actually do this in your head because 10 to the 10th times 10 to the minus 6, you know what that is? It's 10 to the 4th. So you could simplify that so you don't have to deal with all those exponents. All right. Again, you'll have that problem. They're not hard, right? I don't think that's hard. It's just really applying the equation and knowing what the right numbers are, but I don't want you to mess it up because you don't do it wrong in your calculator. Yeah, it will always come out in meters. In fact, if you ever there are a couple of occasions where I give you units that are not standard SI, so just beware of that. Make sure you check your unit. You'll see when you go in to put the answer because I'm not going to put the, like if I ask for centimeters, I'm not going to give you a number that's in meters as one of the options. Okay, so just be aware of that. All right, let's see. All these things are good. Like you have to do all this. I think the chapter 9 stuff is probably easier if you work through it a couple of times. All right, like number 11 is a continuity equation. That's just A1 V1 equals A2 V2. And then that's going to be A1 is 0.5, V1 is 3 equals 1 times V2. So V2 is equal to 1.5. On number 14, you're just doing F1 over A1 equals F2 over A2. But you can just look at it and say, well, look, my area is going from 0.5 to 1 square centimeter, so my area is increasing by a factor of 2. My force is going to do the same thing. So I know the answer has to be C, 40, but it's by this equation that you calculate it. It's going to be 20 over 0.5 equals F2 over the new area, which is 1. Notice here I didn't have to convert my units, even though I gave it to you in square centimeters. The units don't matter here because the centimeter squared, they cancel out in that equation. But if you ever have any question, just convert everything to SI. But I don't think there were any situations where you had funky conversions you had to do. All right. Particular questions? Don't worry about number 8 there. I tried to make chapter 9 as simple as possible since we didn't go through the concept test. They are online, and it might be useful for you to skim through them, but I tried to make it as simple as possible. Number 6, yeah. You definitely have to do this one. This comes up twice, actually. It comes up in the free response where you have to find the net torque, and then also I did it in the multiple choice just to make, for fun. This one's really easy though. Look at this, because this force doesn't provide any torque because it's acting at the axis of rotation, and this force also provides no torque because the angle is 180, right? So now I only have this force, so it's 2 newtons times 3 meters. So the net torque is 6 Newton meters. It's actually negative 6 Newton meters because it's clockwise. I'm actually looking for the angular acceleration. There is a question where I just ask you the net torque in the multiple choice. You have to do that on the free response too. But to find the angular acceleration, remember, just like the free response, in that part I have 3 steps. I first find I, that's 1/12 mv squared for this bar. Not necessarily a bar, although on your free response it is a bar, but you might have to find it for other things as well. That's 1/12 of 2, that's the mass, times 6 squared, that's equal to 6. And then find alpha is torque over I, that's 6 over 6, or 1, it's actually -1. And then, oh, that's it. I want to find the angular acceleration, so C is the right answer. 1 radian per second squared. Okay? That's that. You good? Yeah. On this exam? Yeah. Definitely have to do this. I will give you a shape, and I'll ask you to rank the moments of inertia. The best way to approach it is to first identify the one with the biggest moment of inertia. In fact, I think on your exam, I think I made it so that if you can identify that and one other point, then you can pick out the answer pretty easily. But the one with the biggest moment of inertia is the one with the most mass that is the biggest distance from the axis of rotation. So this one has all of this mass out of this big, big radius. So I know that D definitely has the biggest moment of inertia, and what that gets rid of 3 of those. And then I can just look at the remaining options, and I see they're only different in saying then one of them says that this is equal to this, that these two have the same moments of inertia. Is that true? Do they have the same? They do not. They're not symmetrical. There are 2 points on this shape, or a range of points, that would have the same moments of inertia. I'll let you think about it for just a second. What 2 points on this shape would have the same moment of inertia? Don't answer, just think about it for a second. What 2 points would have the same moment of inertia? Those 2 points would be here and here, or any range of points that are symmetrical along that axis. See, if it rotated about this axis or it rotated about that axis, that would have the same moments of inertia because of the way the mass is distributed, but these 2 points do not, so it has to be B. And then at that point, it doesn't really matter if IB is bigger or smaller than IA. You don't really need to worry about that because you've eliminated all the other options. All right, so B is the right answer. Follow that approach when you on the exam because you'll be able to identify the biggest moment of inertia, I think, pretty easily. Just look for which point has the most mass furthest from that point, and that'll tell you what is the biggest moment of inertia. And then look at the options. Okay. Mm-hmm. This is a pretty good exam. Okay, so I gave you an Archimedes principle problem where you're finding the buoyant force. It's pretty straightforward, to be honest. It's just, I give you a shape and I ask you what is the buoyant force on it. All right, is that clear? Well, let's go and look at this one. I have this rectangular boat that's 2 meters by 1 meter. To what depth is the boat submerged if it has a mass of 500 kilograms? So first of all, the weight of this boat is 5,000 newtons. And that means if it's floating, that the buoyant force is equal to the weight. So the buoyant force, which is 5,000 newtons, equal to the weight, is equal to the density of water, rho Vg. That's equal to 1,000 times volume times 10. That means that the volume is 0.5 cubic meters. Okay? So now this is asking if the volume is, what is the volume is length times width times depth or height. That's 0.5 is equal to 2 times 1 times the depth. So depth is equal to 0.25 meters. So A is the right answer. Okay, yours is going to be a little more straightforward. Yours is going to give you a shape with its dimensions, I think. I think you have to calculate its volume. And you're just going to say the buoyant force is equal to rho times V times G. It's a little simpler than this one. And I would say, hey, you have this boat. What is the buoyant force acting on it? In the course of that, you might have to calculate its volume. I don't remember. But it'll be a simple volume like this, where you just multiply the 3 dimensions. A rectangular boat, not a cylindrical or, I don't know, or spherical or whatever. It's a rectangular boat. All right. Is that clear? Okay, clear. Other particular questions? Five is a good question. Let's just talk about it for a second. So this is similar to your free response, where you're going to have, I think there are 2 spheres that come together. If you look at the fall 24 exam, that's what you have, one sphere that's spinning, and then you engage it with another sphere, and then they both start spinning at the same rate, and you have to calculate what that rate is. Same here. I have 2 bars of the same, their dimensions and mass are the same. That means their moments of inertia are the same. So I know right away that I1 is equal to I2 because they have the same dimensions and the same mass, and they're rotating about the same axis. And initially, only the first bar is spinning, and the second bar is spinning in the opposite direction. And I want to know what is their velocity when they engage. What was the answer to this? Hold on, let me take a look. I think this was a little more complicated. that's a bad question. Let's not look at that one. Okay, I'm sorry. We'll find a different one. It's not a bad question. It's just it's more complicated than I wanted to get into. Okay, yeah. Can we look at 15? Oh, no, not that one. Yeah, this is fine. I'm sorry, y'all. Number 15. Gosh, which problem is this? This is all 21. I have a bar that has a length of 2 meters and 6 kilograms, and it's rotating with that speed. By the way, that moment of inertia would be 1/12 of the mass, 6, times the length, 2 squared. That's equal to 2. And then it turns into a disk. The moment of inertia of that would be 1/2 mr squared. Remember, a disk is just a what on your equation sheet? You know, remember?
Yes.
A cylinder, right? A cylinder about this axis. There were 2 cylinders, one about this axis and the other about this axis. If you remember, the one about this axis was really complicated. It had 2 terms. So a disk or a flywheel or a merry-go-round, all those are cylinders. All right, so this I is 1/2 of the mass, which is 6 times 1 squared. That's equal to 3. So this bar with a moment of inertia of 2 is expanding, fanning out into a disk with a moment of inertia of 3. And I want to know the rotational speed of the disk. So I'd say that L1 is equal to L2. I1 omega 1 equals I2 omega 2. That is 2 kilogram meters squared times 3 revolutions per second is equal to 3 kilogram meters squared times omega 2. Solve that for omega 2, and it's going to be 2 revolutions per second. You'll have questions, a couple of questions like that. One in the free response, which is actually going to be worth 2 questions, 2 multiple choice questions. And then you have at least one in the multiple choice. So it's 3 questions that are similar to that. Is that clear, or did I confuse you? Now computers can do that before? Huh? Yeah, you need to practice it. Like, I can do it here all day, but if y'all are practicing, it'll be a difficult exam. But it's not a hard exam. It's really not. Like, if you just put a little bit of practice in, you'll be fine. What else, y'all? Other particular questions? Peter?
Why would your radius be 1 for the?
Oh, good question. Because this for the bar was not radius; it was the length of the bar. But see, that bar fans out, and it makes a disk with a diameter that's 2 meters. And so to find the moment of inertia of this, I need not the length or the diameter, but I need the radius. Read on your equation sheet, like on that table with the moments of inertia, it describes what each variable means. B is the length, R is the radius. Okay? Be careful of that. I think that comes up. I don't remember if that's relevant for tomorrow, but be careful. It might be important. Kate, you were about to raise your hand, weren't you? Number 6. That is a chapter 7 question. Yeah, so you're not going to have to do that. Okay? You want me to do it anyway? No, I don't need to do it. You want me to do it? No, it's not on these things. It's chapter 7. Not relevant. Now, there will be a kinematics question in the free response with the very first question when you have, like this one right here, where I just ask you the angular speed of the bar. I ask you first, what is the net torque? And then I ask you the angular speed. You do need to know that equation. It's omega equals omega naught plus alpha t. I mean, that's on your equation sheet, but that's back in the chapter 7 stuff. Okay? So just be prepared for that. I do ask for omega, not for theta. Just to, be prepared. All right? What else, y'all? You ready? How many exam 2?
We have our
Your final?
on 30.
Okay.
So,
Okay, good. Y'all good? You bored?
I'm still confused on 16.
Okay, let's-
Oh,
Was that the one that I started and I said, no, don't worry about it?
oh, you said don't worry about that.
No, which one? Which one was 16? This one? Oh, this one. Okay. Let me erase everything and then I'll just try to start over and just try to, I get it. It's kind of tricky to understand, but let me look at your exam and see what, you mind if I look? Just a second. Y'all like it when I pull out the exam, don't you? Do you like that? Oh, do I have? Oh, yeah, I have it. Better have it right this tomorrow. Let's see, that answer is B, that answer is C. Okay, let me ask you a question. If I have two objects and they have the same angular momentum, you hear me? And one of them has more energy than the other, which one is going faster? The one with more angular, with more momentum, or the one with less momentum?
It's more.
Yeah, it's the one with more. The one, let me write that down. Two objects have the same angular momentum. Same angular momentum. One is going faster, or excuse me, one has more energy. Which one is going faster? That's the question. The one with more energy is the one that's going faster. Because L is equal to I omega, and kinetic energy is equal to 1/2 I omega squared. If one has more energy, it's because omega is bigger and I is smaller. That is, that omega is, say, bigger by a factor of 2 and I is smaller by a factor of 2. But if omega is bigger because of the squared term, the kinetic energy is bigger. Let me repeat that question. It's the question you're going to see tomorrow. Two objects have the same angular momentum. One has more energy than the other. Which one is going faster? Which one's going faster? The one with the more energy or the less energy? Or more energy. The one with the lesser energy actually has a bigger moment of inertia. But the one with more energy has a bigger speed. Is that?
So you're not gonna be asking something like that. You're
No.
gonna be asking what was going fast.
Yeah, this one, like I said, this one's a little more complicated. Does that help? Okay. Does that help? Yeah, you get the question again? Two objects have the same angular momentum. One of them has more energy than the other. Which one's going faster? The one with more energy. All right. Other questions, Joe? Going? Peter?
B, we have 13 on this as well.
Okay, yeah, so these are hard, or people have these. First of all, identify the one with the biggest moment of inertia. That would be, which one? C. Right, so that gets rid of a bunch. That gets rid of that one, and that one. And then identify the least moment of inertia. Well, that's going to be the one right in the middle, because it decreases the distance to all the points, but that doesn't help us. So now we need to separate these two. Which of those has the bigger moments of inertia, D or A? D is right, yeah. Because D, look, D has all this mass out of this really big distance. But A, you only go out, you know, about half that distance. So D definitely has a bigger moment of inertia. So that gives me A is the right answer. Okie dokie? We're good? In the last minute? Yeah, okay. I mean, Emily, sorry, Emily? 4 on 22. Which one is this? Okay, you're going to have one of these too. I'll ask, you'll have some questions where you have to calculate moment of inertia for shapes, but this is the moment of inertia for particles. You'll recognize them because either I'll use the word particles and arrange them in 3 particles, or you'll recognize it because the axis of rotation will be outside of whatever the mass is. Here, the axis of rotation is outside of the object. And also, I won't give any dimensions for the object. And in a group of particles, the moment of inertia is just given by the sum of mr squared. That is the mass times the distance from the axis of rotation squared. So that's 4 times 3 squared plus 5 times 2 squared. And then that last one, since it's on the axis of rotation, it would be 2 times 0 squared, so just 0. So I don't need to do that. So that's 4 times 9, 36, plus 5 times 4 is 20. So it's 56, D, right answer. All righty. All right, folks, that's it.